on, and I'm going to go ahead and share my screen. All right, so here we are with graphs of sine and cosine, okay? So I know we've kind of stepped away a little bit from this what we know and what's new platform, but I thought this is a good time to kind of bring it back, okay? So before we get to graphs of sine and cosine, let's remind ourselves of what sine and cosine and tangent actually stand for. And so we know that sine is opposite over hypotenuse. We also know that it's the y value on the unit circle, right? That's not new. We know that cosine is adjacent over hypotenuse, and that's the x value on the unit circle, and that's not new either, okay? We learned that in chapter 5. And then the last thing about tangent is we know it's opposite over adjacent, but we can find it by using the y value and the x value together to find the ratio, and that will give us tangent. Okay, so tangent requires a little bit more work than just going to the right angle on your unit circle and finding an x or y value. You actually have to divide those, okay? And then below here, I just inserted a little picture of the unit circle. I saw that on pretty much everyone's reference sheet on exam 1. Which is great. And as we sort of move forward, I want us to think about like, yeah, it's kind of a pain to draw it all out, right? And so how can we challenge ourselves to start to move in a direction where what we're focusing on is this first quadrant of values? And in theory, if we know these values, how can we find all the other values on the unit circle so that it doesn't necessarily take up as much space or take up as much time when we're writing it, but that we're really looking more for those patterns that we see here, okay? All right, so that's what we know. And what's new is a bunch of questions that I hope we have answers to by the end of today's session. Okay, so what does the graph of sine look like, and how does it relate to the unit circle? And then similarly, what does the graph of cosine look like, and how does that relate to the unit circle? And then how do we find characteristics such as domain and range? And that should sort of sound familiar because we've talked about domain and range before, but we're also thinking about new phrases like amplitude and period and wavelength, okay? So we've got some new vocabulary to layer on. And finally, we're thinking about how do graph transformations apply to sine and cosine, okay? And so that's why we did that classwork activity about graph transformations of parent functions. Now, a few of you emailed me and said there is nothing to submit at the end of that Desmos activity that we had for classwork. There's nothing to submit, but on my end, I can see what you put down for every slide. Okay, so it automatically submits it for you. So that's how I can go back in and check. You don't need to submit anything. So if you were nervous about that, don't worry about it. Unless you just skip through the slides, then I would be nervous. Okay, so that's what we know, and this is what's coming up, okay? All the things that we're gonna learn today. And so what we're gonna start with is just the graph of sine. And we're gonna take some time to look at the graph of sine, and then we're gonna break out into some small groups and work with Desmos together, where we're inputting certain things into Desmos so that we can use it to think about what's happening to the graph, okay? So here we have a graph of sine. So if I put sine x into Desmos or any graphing tool, I should get a picture kind of like this, okay? And we'll talk about what things we might need to be careful about to make sure our graph looks like this and not just a straight line. Because I bet if some of you are graphing right now, you might end up with the straight line, okay? So based on this picture, let's see. Let's actually start with the range here. So the range, as a reminder to those of you who might have forgotten, is really saying the collection of all possible y values in this function, okay? And when we look at the graph of sine, we notice, I hope, that it kind of goes up and down, but it never goes like super large in terms of a y value, and it never gets super small in terms of a y value. What might we say is the range of sine based off of this graph? Like, what are the y values that this graph is showing us? One, Vanessa, like one being the highest value? Yeah, I would agree. Vanessa's spot on there. One is the highest value. And now let's maybe think about the opposite of her question, which is, or her answer, which is, what is the lowest value we see here? Right? Perfect, right? We've got this graph sandwiched between -1 and +1. And so what that means is that our range for sine is including, so we use a bracket and we're very clear about our bracket, from -1, because that's the smaller value, all the way to +1, and we close it with a bracket, okay? So because our range stays between those two values, we can say that it's only from -1 to 1. It's not any other value. We can't have 2, we can't have 5, we can't have -1.5, only values between -1 and 1. And the reason why that is because the unit circle, our good old friend the unit circle, has a radius of 1. Right? So if the circle has a radius of 1, that means that none of the x values should be bigger than that. That would be weird. It would be off the circle, okay? So that's why our range is from -1 to 1. Now, if we think about the domain of this function, all right, I will tell you this. I just took a snapshot of sort of the middle part of the graph here, but the waves continue in both directions. So like it continues to go up and down, up and down, up and down, all the way to the right, and it goes up and down, up and down, up and down, all the way to the left. So knowing that, what do we think about the domain of our sine function? Or in other words, what do we think the x values are that make this sine function? Yeah, exactly. We're looking for -infinity to +infinity. And Christina, that is exactly my next point. We want to use parentheses. And the parentheses is because technically we can never get to infinity. Okay, we can't get to infinity the same way we can get to 1. So that's why we use the parentheses. Okay. Now, for those of you who are new, or just maybe to kind of refresh this piece, another way of saying this is this fancy script R, which stands for all real numbers, okay? And so as we move forward, like I want us to know the -infinity to +infinity notation, but we also want to know that's the same as when someone says all real numbers. Okay. All right. So let's talk about even, odd, or neither. What do we know about sine in terms of even, odd, or neither based off of chapter 5? I know some of you wrote about this in that question 6 where you got to choose which topic you were going to explain, right? So what do we know about sine in terms of even or odd or neither?
It's odd, and a way to like confirm it is that if you go to your x value, if your x value was -pi/2 and pi/2, you can see that their y values are different.
Okay, so sine of pi/2, let's actually use this graph. When I go to pi/2, what is the y value there? Well, I go to pi over 2, and the y value is 1. Okay. And if I go to sine of negative pi over 2, that would be like here, that y value is negative 1. Right? And so when we go plug in positive x and negative x, and our answers are almost the same except their signs are different, that means that it is odd. Okay? And so this is just an extra confirmation that sine is an odd function. Now, this graph that we have right here, is this symmetric about the y-axis? Like if I take the right half and the left half and I fold them together, are they going to be the same? And I think we would agree that the answer is no, right? One side goes up and then the other side comes down. So we know that it's not symmetric about the y-axis, but here we can see that it's actually symmetric about the origin because they go in opposite directions, right? Okay. We've got one last vocab term here, and that is something called period, okay? So what period is asking you about is how long is one wave, okay? So when we say period in terms of sine and cosine, what we're really asking ourselves is how long is one wave, okay? And so if we think about the graph that we have right here, let's maybe trace one wave and see what happens, okay? So if I start from here and I trace one wave, is this one wave? What do we think? You see a couple no's. Yeah, that's not one wave, right? What about if I just keep going and now I'm like, back to the x-axis? Is that one wave? No. Okay. I would say maybe that's part of a wave, but like I'm missing all of the negative values, right? A wave should mean you get every value that kind of comes out of there, meaning all the positive values and all the negative values. And so if I keep drawing, now I've got one wave, okay? Exactly. And Thea, you are correct that the distance here along the x-axis is 2 pi, okay? So in this case, our period is 2 pi. Because that's how long it takes us to kind of get around to the same place again in the unit circle, all right? Yeah, we're going to talk a little bit about frequency. Yeah. All right, so are there any questions so far about sine and its domain and range and being odd and the period? Before we move on, let me ask you one more question, okay? Let's say that if I was trying to find the period and I wanted to trace one wave, and I trace this, that pink one, is that one wavelength? Yeah, that's one wavelength too, okay? Now let me erase this one for a moment. And let's see, what about this? So let's say I started up here and I traced all the way down and I went all the way back up to the top. Is that blue one wavelength? Ooh, conflicting answers. A no and then a yes followed by a, oh, shoot, am I wrong? So the period, like how long did that take to go from the first blue point to the second blue point? Well, I know we don't love fractions, but let's kind of take a look at this. So I start here and I go all the way to here. So from negative 3 pi over 2 to pi over 2, yeah, that's a distance of 2 pi. Okay. So what makes people say it's not a wave? Like, why is the blue one different from the pink one or the yellow one? Tell me more about that. What do you mean about the starting and ending y value? Hmm. Well, let's see. Let's go back to the yellow one for a moment. Okay, if we start with the yellow one, we knew that we started at a y value of 0. And we went up, we went down, and we went back to 0. So wherever we started with the y value, when we stopped, that had the same y value, right? At 0, the y value is 0. At 2 pi, the y value is 0. And I got all the positive values, and I got all the negative values, okay? But if I took this blue piece, I start at 1, that means when I end, I should end at a y value that is also 1. So I go down, I come up. Sure looks like I start and stop at the same y value. Okay. Well, I think that the yellow one, if I erase the yellow one, just as a standalone, is the blue one a wave? I'm not saying if together they're like both waves, but like, is the blue one by itself a wave? Okay. Now, this is something I really want us to think about, but this blue one is also one wavelength. Okay. Yeah. So wherever I start, I just have to stop at the same y value. And I have to make sure to get all the positive and negative values in between there, okay? So let me, all right. So what we're gonna do now is this, okay? We're gonna we're gonna do this first one together, and then we're gonna move out into some breakout rooms to practice sort of the other ones, okay? But the question here is, we're taking a look at some value in front of the sine function, okay? So for 1, I have y equals 2 sine x. Okay, let's get. And then for the other function, I have y equals 1/2 sine x. And my question to you folks is, what do you think is going to change about these graphs from the original? So let's say our old school one is y equals sine x. So what do we think that 2 is going to do? And what do we think the 1/2 is going to do? Okay, so we've got a couple of ideas. The y value of a parent function, they're going to be multiplied by those numbers. Okay, that we compress the waves. Gloria, can you tell us more about what you mean by compress the waves? Okay, so maybe there's going to be more waves, so more frequent. Instead of spread out. I think those are A values. Yeah, they are A values. Okay, stretch the wave. Thea, when you say stretch the wave, do you mean like how Gloria was saying, like you sort of like stretch them sideways? Or what do you mean by stretch the wave? Okay. Okay, so like more waves or maybe stretching the wave sideways. And Natalia, what do you mean by amplitude? Okay, so you're saying stretch the wave, but maybe like this way, like vertically. Okay. So these are all good ideas. And this is something that when you move into the other activities, I do want you to take at least a minute to just chit chat as a group and figure out what your predictions are before you go to Desmos, okay? So then after we come up with these ideas, let's use Desmos to figure out what's true or not, okay? And so what we're gonna do is you're just gonna hop on Desmos. Where did my mouse go? Okay. And let me share that screen with you. Okay, so I'm gonna shift gears here a little bit. Let's read some directions before we go. So we're gonna be sure to set our x-axis to -2 pi to 2 pi, right? That's one thing we need to do. We wanna change our step to be pi over 2, and we wanna click on radians. So those are 3 things that we're gonna do when we get into Desmos. We're gonna set the x-axis, we're gonna set the step, and we're gonna click on radians, okay? So let me, okay. Do we see the Desmos screen right now? Yeah, okay, cool. So where do we change all these things, okay? You see this little wrench in the corner? That's where we're gonna click. So this is your settings, okay? So we click on that, should look like this. And the x-axis, you see how it's from -10 to 10? This is where I'm gonna change it to be -2 pi to 2 pi. So the way we do it, let's say you accidentally erase it all. If you type in the minus sign, which is next to the 0, I think at least on keyboard, and you type in 2, that would be -2. But if you want 2 pi, you literally just type in pi and it will change it to a pi for you. Pretty cool. And then that's the -2 pi, and I want to change the 10 to a 2 pi. And again, I type 2, and then pi will turn it into pi, okay? So that was the first thing that we needed to change. The second thing we needed to change is this step part right here. The step means how much are we counting by, all right? Now, if you look at the way this is set up right now, my screen goes -2 and then -4 and then -6, and then it kind of stops because it's at -6.28, which is about 2 pi. But I want to count by pi's instead because it's actually a little bit easier for us if we count that way. So I'm going to set my step to be pi. You see how all of a sudden we have pi's come up? Pi divided by 2. Okay, so we're setting the graph to help make our lives easier, all right? The last thing we want to do here, we want to make sure we're not in degrees, but we are in radians. So the radians should be green, okay? Everybody got those settings? understand where to find them, how to change them? Okay. All right, so I'm going to close that part, and I'm going to go over here, and I'm going to type in my first equation. And I'm going to type in y equals sine x, just so I get a picture of what that looks like, okay? And so I'm going to draw this on my grid. And so the way that I'm going to draw it, I'm going to follow the points that we're given here. So one point that I put down should be 0, 0. We want to draw that accurately, okay? And now let's kind of keep moving to see what other important points there are. Well, this point up here is pi over 2, comma 1. So I'm going to go to pi over 2, and I'm going to go up to 1. Okay. Then I'm going to keep going. Pi, comma 0, 3 pi over 2, comma negative 1, and 2 pi, comma 0. Okay. So I should have one wave on the right-hand side. And then I'm going to do the same thing on the other, 0, and then negative 1, and 0, and 1. And I'm going to draw those in. And then I'm going to try and connect them with a nice smooth curve. Okay. It's going to look a little bit bigger on your graph because I think we have it set to be -2 to 2, right? So your wave should look a little taller. It should look something like this, okay? All right. So now let's type in 2 sine x and 1/2 sine x, all right? So I'm going to keep this one here. I'm going to hit enter or return. It's going to cue me to write a new function, and I'm going to write y equals 2 sine x. And that one is the blue curve, right? So they tell you what color is which one. The red one is the original. The blue one is your second one, okay? So let's go ahead and see, like when we graph this one, what's going to be different about what we type in or what we draw on our grid? Like what are some things that stay the same and what are some things that change? The x's are the same, yeah. And what happens to the y's? Ah, the y's increase. Okay, do all of the y's increase? Maybe that's a better question. Do all of them get bigger? All the zeros don't. Okay, so for example, like this point, yeah, is still the same, 0, comma 0. But this point way up at the top is at pi over 2, comma 2. So those do increase, right? And we could say similarly, the ones that are negative get more negative. Okay, so I'll give you a moment to draw these on your grid. And I like that observation there. That is, the 0 values stay the same, but that all the other y values, what was the phrase that was used again? The y values will be multiplied by 2. And so we should get another curve that is a little bit taller than the original curve, okay? All right. So based on that, let's revisit our prediction. What do we think is going to happen when we type in 1/2 sine x? The y values are going to decrease, okay? And so let's see. Y equals 1/2 So as soon as you type 1/2, it turns it into a fraction for you, okay? So 1/2. Now, we don't want to keep typing like with the 2 because that'll be underneath the fraction line. We don't want that. So we need to make sure to move over and then type in our sine x. And that one's our green curve, okay? So let me get rid of the blue one for a second. I'm gonna click on this circle, just so I'm gonna hide it for a moment, and now we can compare the original with the green curve, okay? And so I think we can see here that the predictions, the revisited predictions are true, that our wave is now maybe a little bit shorter than it was before, okay? And so the points that we're gonna make sure we have here, instead of going up to 1, we're gonna go to 1/2. And instead of going down to -1, we're only gonna go down to -1/2, okay? All right, so I'll unhide the blue curve again, so we can kind of see all three together. All right. And I'm actually going to switch screens again. I'm going to put the iPad back on so we can take a look at the next questions that we have, okay? Okay. So at this point, your notes should look something like this, right? Whatever colors, or if you don't have colors and you want to choose a dotted or solid line, that's fine too. But we should see that we have three different graphs, that the blue one is our sine, our original parent function, and then our two sine x, those go up and down a little bit higher and lower, and then our 1/2 sine x goes up and down a little bit less, only half instead of 1, okay? And so what I want to take a look at next is one other cool feature about Desmos, okay? So what we're going to do, we're going to go back into Desmos. We're going to clear out the previous functions, and instead we're going to type in this. Oops. We're going to type in y equals capital A sine theta, or sine x. Now, as soon as we type that in, there's going to be an option to add a slider, and that's what we're going to do. Okay, so we're going to add the slider, and then we're going to be able to slide that around to answer these questions. Okay, so you go ahead and type that in, but keep these three questions in mind. What happens to sine when A is greater than 1? What happens to sine when A is between 0 and 1? And what happens to sine when A is negative? Okay? So I'll give you a moment to go into Desmos, kind of play around with the slider, and then we'll come back together and answer these questions. Right, so as soon as I type in that capital A, it says add slider, and I just click on that. And now this allows me to kind of move around that slider. Okay. Now you can sit and just kind of slide it around and wow, that's like a lot of things changing, right? But the goal is that we want to be more descriptive in our language. And so let's look at that first question, which is what happens to sine when a is greater than 1? And so instead of just like moving the slider, so like we could move it to 1 and then just move it this way, right? That would be one way to do it. But if you want a more precise way, what you could do is if you click on the 10, okay, you can say I want a to start at 1 and I want a to go all the way to 10. And now you're controlling how far your slider moves, okay? So now my slider goes from 1 to 10 and I can use that to answer the question. So I slide this around and what do we think? What do we want to say is happening to this graph? So what happens when a is greater than 1? Right? What happens when a is greater than 1? Yeah, I agree. I think we could say that there is a vertical stretch. Right? So that's what I'm going to write down under letter A in the notes. What happens to sine when a is greater than 1? I'm going to say that there's a vertical stretch. Okay. Now let's maybe change these values to answer the second question, which is what happens when a is between 0 and 1? Okay, so we can make that happen too. We can make our slider only go between the small value from 0 to 1. So let me actually change the size of the y-axis again. Okay, so this is that 1. What happens? Oh, shoot. Ooh, oh. Right? Yeah, exactly. Instead of stretching our wave, we're now compressing it or making the waves shorter. So vertical compression would be a good way to describe what happens when a is between 0 and 1. Okay. All right, and then to answer the last question, what happens when sine is negative? Well, I could go back in here and I could go from negative 10 to 0, right? And then slide it around. What's happening to this graph? Is this the same or different as when a was positive? It's different. Okay, maybe let's put in y equals sine x, just so we have a reference to that. You can change the color. So if I click on this and I hold it, I can change the color. So let's maybe change the original one to purple. Okay, and now, yeah, exactly. It's a reflection, right? Let's see if I can get it right at 1. Oh. So the purple one is the original, right? It goes in all the places that the original goes up, the negative one goes down. Oh, am I not sharing that? I'm still sharing that. So sorry. Okay, what is happening with my sharing situation here? Okay, now can you see it? Sorry. Yeah. All right. So so let me know if you cannot see what I'm looking at. But for all the purple ones here, right? This one goes up, but the red one goes down. Okay. The red one goes up and the purple one goes down. right? So they're opposite of each other, or we could think about it exactly like what Brian said, which is that it's a reflection over the x-axis, okay? All right, so let me change my share again, but change it to the right thing. Okay, and so this is all I wrote down for the answers. What happens to sine when a is bigger than 1, when a is less than 1, or when a is negative, okay? But I do want to bring in Natalia's word that she mentioned earlier and talk about how it relates to the graphs that we've seen, okay? So if we go back to the graphs, there is something called the amplitude. And the amplitude tells us how tall each wave is, okay? But one thing that we need to make sure we understand about the wave height is it goes from the midline to either the highest point or the lowest point. So this right here is an amplitude of 1, because from the center to the highest point of the blue curve is 1 unit up the y-axis, okay? Now knowing that, what is the amplitude of the orange graph? And what is the amplitude of the green graph? Yeah. All right, so we got an amplitude of the orange one being 2, and the amplitude of the green one of 1/2, okay? Well, hang on a second. Those numbers are pretty familiar. In fact, wasn't 2 the number in front of sine and 1/2 the number in front of sine? Sure was. So this 2, whoops, this 2 tells us about the amplitude of the wave. And this 1/2 tells us about the amplitude of that wave. Now, what number is in front of the sine x here? It's a 1. And guess what that 1 tells us? The amplitude of the wave. Okay, so that number in front is pretty significant. It tells us sort of how tall the waves are going to be from the midpoint. So if we kind of go back to our original predictions, we might say that, yeah, the y values are going to get multiplied and that there's sort of an amplitude change happening here. Things are stretching vertically, right? We're going to save the horizontal stretching for one of the other things that we're going to explore. But does the flow of this activity kind of make sense to you? Yeah? Okay, so you're working together, you're just, thinking about what's happening, but I think it's important to be able to make predictions and then kind of use the technology to see if that's true or not, okay? I also think that Desmos is such a powerful tool that I want us to feel comfortable using it for all of the cool things that it can do for us, okay? All right, how are we feeling out there? All right. So just to kind of talk about what's going to happen in a little bit, you're going to notice that there is another set that asks you to play around with another value. So the numbers are the same, 2 and 1/2, but they're in different places than they were last time, okay? And you're gonna take some time to explore those, all right? There'll be some questions for you to answer, but very similar. You're gonna take a look at another number in a different place, and what does that do, okay? And same thing, graphing everything, sketching whatever comes up on Desmos, okay? So I'm not asking you to graph anything on your own. We're using Desmos and then kind of copying the main point. And then there'll be one last one, which is another place where there's a number and what would you like? What do you think that number will do? And then you're gonna sketch the graphs to kind of convince yourself of what's happening there, okay? And then when we come back together, we'll debrief that, make sure that we've hit all the important points. And then we're gonna have a chance to kind of practice the graph transformations in sort of a step-by-step, like what's happening and in what order, and not just that Desmos magically gives us the answer, but how do we kind of predict from the pictures or from the equations what's gonna happen, okay? Okay. All right, so that being said, I think this is a good time to take a break, okay? So I'm gonna stop sharing my screen. We're gonna take a break and...
Oh, Professor?
Yes.
It's Vanessa's birthday today, and I was wondering if we could sing happy birthday to her as a class.
Christina's.
Oh, Christina. Oh, I said, I'm so sorry. Oh my God.
It's Christina's birthday.
Oh my. Just cut the break. Oh my God.
Well, happy
I'm so sorry.
Christina. Thank you for gracing us with your presence during your birthday.
I'm so sorry, Christina.
Are you gonna sing for us?
Oh, sure.
Oh.
I thought we could do it as a class, but I could sing as well.
I think that this might be the one time. Here, let me stop this recording. All right, folks. I think everyone has made it back safely. Okay. So how did that go? Was that enough time? Not enough time?
That was enough time.
All right. So let's take a look real quick at some of the results, okay? So for B, you should have gotten something like this for your graphs, right? Where the blue one is your original, the orange one, there were more waves, and then the green one, there was less waves, right? And so what I'm wondering is when you folks were discussing what happens to sine when B is greater than 1, what did you say? What were some results that we put down for that, or patterns that we saw? And does what we have here kind of match? That we have more waves when B is greater than 1, but less waves when B is between 0 and 1? Yeah. Yeah. And so when we're thinking about that center point, this is like our y-axis, right? Like the vertical line that goes through our center point is where things flip-flop. Okay, just to kind of clarify. All right. But one thing I really want to draw your attention to is that the numbers in the equation actually tell us more than what, like that there's more or less of them, Okay, so specifically in this orange one right here, where it says sine of 2x, this 2 means that there are 2 waves where there was 1. Okay, so if you look at the orange one, there are 2 waves. If I go up and then down and then up, that's 1 wave, right? But I'm not done with the wave of the original one yet. So I go up and down and up. And it turns out that that number not only tells you that there's more, but it tells you how many more. So if there was 1 wave there before, now there's going to be 2, okay? If we change that number to 3, sine of 3x, how many waves are going to fit in that same space as where there was 1? Well, it's going to be 3, okay? And now this one, this 1/2, tells us that there's a half a wave where there was 1, okay? So I want us to not only say stretch and shrink or stretch and compress, but I want us to know like how many there are going to be, okay? Are there any questions about that? Yeah, exactly. That tells us the frequency, right? It tells us like how many we're going to have or how frequently they're going to happen. Mhm. All right. So if we take a look at part C, this was when we had like the x minus pi over 4 and the x plus pi over 2, okay? So if we look at the graphs, the amplitude did not change. The frequency did not change, but things shifted left and right. Okay, now we've got a newer word for this that I put down here in the patterns. Okay, we have something called a phase shift. And the phase shift is the same thing as when we learned about a horizontal shift. It's the same thing, okay? So phase shift is the same as horizontal shift, okay? So we've got a phase shift to the right and a phase shift to the left. And one thing that I am going to do on the answer keys is I'm going to make sure to highlight the center point. So for example, the center point of the blue point is here, okay? And then the next point, sort of the next nice point is here. So like if we keep track of where these blue and purple points move to, in the orange equation, the blue dot moves to here because we move pi over 4 to the right. And that purple point on the blue one should move to here, okay? So we can see when we look at a couple points that we can see the whole graph slides to the right. And then if we look at the green graph, we can see that that one slides to the left, okay? So this one is our right pi over 4. And this one is our left pi over 2. Okay? So very similar to the stuff we learned in 116 if you were in 116, but now we're just looking at it in terms of a sine graph. Okay? And then the last one that I asked you to take a look at, which I didn't get a chance to finish here, but someone want to tell me what happens when we have that +1 and the -1 next to the graph? Or next to the equation, rather? Right, so we have our graph of sine. And my question is, what does that plus or minus 1 do? Yeah, those are our vertical shifts, okay? I always get so nervous when I say that word because I'm afraid I'm going to leave out the F, and it's definitely happened before, but I'm trying to be really careful. So for the first one, the y equals sine x plus 1, that means we're going to take all of these nice points and we're just going to move everything up 1, okay? So I'm going to use the nice points because I don't want to try and count fractions if I don't have to. And so if I think about this center point, well, that center point is going to move up 1. And if I think about the point next to it, that one is also going to move up 1, right? Does that make sense how I'm just taking points and shifting them? And when I move them up 1, it's going to give me something kind of like this. So the shape looks the same. The amplitude is the same. The number of waves is the same. But all I've done is slide the picture up 1 unit, okay? So this one is our sine x plus 1. And then if we were to do the sine x minus 1, well, we would take the blue and purple dots from the original one and we'd move them down 1. We'd move them down 1. And then we'd kind of sketch around that. Move every other point down 1. And, whoops. Okay, something like that, right? Sine x minus 1, okay? And so when we look at what happens if we have the d value or the number at the end larger than 0, we're going to have a vertical shift up 1 or up. And then if the number is negative, we'll have a vertical shift down. All right. Any questions on any of these little explorations or playing around with Desmos? Oh, sorry. My question was, were there any questions about any of these explorations, like what the A, the B, the C, or the D do? No. Okay. Yeah, so this is definitely very similar to all the graph transformations we did before, except we just have a new graph to look at, okay? That's really the only difference. But one of the things I like about the graphs of sine is sometimes it's actually easier to see what's happening because we have this pattern that repeats, and then we can see how that changes the whole pattern, okay? So if we're feeling pretty good about that, let's take a look at some of the practice questions. Yeah, okay, yeah. Let's take a look at some of these practice questions. And the format of these is going to be pretty similar to what I might ask on an exam or what I have on the quizzes. So let's make sure we understand the format of what's happening here, okay? All right, so in this situation, what we're looking for is to break down the different components and kind of predict what's going to happen based on the numbers. Okay, so the goal here is not to go straight to Desmos and try and figure out where that graph came from, but the goal is to really look at the equation, say, all right, I know what the 3 does, I know what the 2 does, and then be able to graph it on our own, okay? And so if you were in Math116 with me, then you know that not only do we have sort of this A, B, C, D in terms of graph transformations, but that they happen in a specific order. So they occur in the following order. And that is, we're going to take care of any C's first, and then any B's, and then any A's, and then any D's, okay? And so when we look at our equation, we might notice that we have a 3 in the front. And which letter does that correspond to? A, B, C, or D? Good, exactly. That 3, corresponds to our A. And what that means for us is we're going to multiply y values by 3, okay? So we could think about it, we're stretching out the tops and bottoms of each wave. But that's not gonna be the first thing we do. That's actually gonna be the last thing we do, okay? Before we do that, because A is towards the end, what we are gonna do is take a look at this 2, okay? So which letter is the 2? Is that an A, B, C, or D? Yeah, that is a B. And so what that means, if we interpret this in words, is there's going to be 2 waves where there was 1. Okay, so everything is going to go twice as fast, kind of like how our class goes twice as fast as a regular Math 104, because we're in 8 weeks, right? So our class goes at twice the pace as a regular class. All right, so that's a good start. We sort of annotated our equation, we figured out what the things do, and now we just need to do it piece by piece, okay? Now the parent function here, for the equation, we just want to write f of x equals sine x, okay? I like to summarize that as taller and a compression. Yeah, that's fine. That's totally fine, okay? So one of the things I want us to get used to is not just our parent function of sine as the equation, but I want us to be able to graph this fairly quickly, okay? So when we start our graph, sine goes through the origin. So that's sort of the first point that I want to draw in there is the origin, okay? Now at pi over 2, I should go up to 1, right? And then it goes back down to 0, and then -1, and then 0. Okay. So even if you don't like the pi on the x-axis, it's really there to help make your life easier rather than being, I'd like you to graph an x value of 3.14159, right? That's like a really gross looking decimal, but when I call it pi, it makes it a lot easier to count by on your graph. And so we're going to draw this side, okay? And then since we know that sine is odd, we're going to go down on the other side before we go back up. So they're going to go in opposite direction. Now we have our sine graph, okay? Definitely something you want on that reference sheet for next week's exam is like the parent function here, okay? Now, the next thing that happens is the b. All right, so from our parent function, now what we're going to do is we're going to make 2 waves where there was 1, okay? So over here in this first box, I'm going to write exactly that, 2 waves where there was 1, okay? And the part of the equation I write is f of x equals sine of 2x, because I'm just taking care of that part first. And then our last step will be, then we're going to multiply all the y values by 3, okay? So like I said, on the answer keys, I put like a center point, right? And then I also put a like a point next to it, so we could kind of keep track of some points as we go instead of just like drawing some waves and hoping for the best. Okay, I'll tell you right now, if that's your approach, you're like, oh, I'm just gonna draw some waves and hope it works out, you're not gonna get credit for that. Okay, so I really want us to show that we understand what transformations are happening here. So now here's the thing about the center point. If I'm just compressing things, I'm compressing around the center point. So that center point is going to stay. Okay, so that center point, that blue one, stays. But humor me for a moment. How many boxes did I go over to get from the blue point to the purple point? I went over 2 boxes. Okay. And how many boxes did I go to complete 1 wave? I went over 8. Okay. Well, if 1 wave fits in 8 boxes, and now I need 2 waves in 8 boxes, how many boxes will it take 1 wave to happen? 4, exactly. So I'm gonna just say that from 0 to 4 boxes over, which is pi, is gonna be 1 wave. And then from pi to 2 pi is gonna be another wave. Okay, so in the top picture, I have 2 waves. I have one on the right-hand side and one on the left-hand side. But in the second picture, I need to have 4 waves, okay? Now, the way that we kind of graph them, 2 waves in 1 means that it happens twice as fast. So this purple point, we want to scooch in. Instead of being 2 boxes away, we want it to be 1 box away. And I scooch everything else in, and look at what I have. 1 wave, and then I have another wave. 2 waves in the place where there was 1. Okay. So let me just pause here for a moment. Are there any questions about where I got like all of the other points from?
So we move the purple point to just 1, and then we move all of the other points accordingly?
Yeah, so we took 2, and because we had to squeeze more of them in here, that distance only became 1 box. Okay. Can we just multiply by 2? What do you mean by multiply by 2? So if you're multiplying the x value by 2, I think that you're gonna find that to not be necessarily helpful in generating a picture, okay? The y value, like the 3 in the front, we'll be able to multiply that. But the x values are always a little weird. They're like the opposite of what you think they are, right? Because if we need 2 waves, everything needs to be closer together. Right, so our points are half the distance apart, okay? And if we kind of finish that off, we've got something like that, okay? So in the first picture, we had 2 waves. In the second picture, we had 4 waves, which is good, because that's what we said. We wanted twice as many waves, okay? Now our last step is to go ahead and multiply the y values by 3, okay? And so that is our full equation, 3 sine of 2x. All right, so let's start with this center point here. What's the y value of the center point? It's 0. What's 0 times 3? 0. Guess what? That center point stays. Okay. All right, what's the y value of that purple point? 1. All right, what's 1 times 3? 3. So now my y value is not going to be at 1, it's going to be at 3. Okay. Did I go up 3 from this purple point to get to my next point? Like it had a y value of 1, it went up to a y value of 3. I did not count up 3 units, okay? But I did multiply by 3 to get the new value. All right, if I keep going, 0 times 3 is 0, negative 1 times 3 is negative 1, 0, 3, 0, negative 1, 0, or negative 3 rather. And if I do that all the way across, whoops. I get taller waves, right? Which I think is exactly what Natalia said. We would get taller waves, so the amplitude is different. Sure. So what I did with the 3, I took the y values of all the points that I had in the second graph and I multiplied them by 3. So the y value of that purple point was 1. 1 times 3 is 3, so that gives us this new purple point on the next graph. Okay. If we took another example, what's the y value of that yellow dot? Right? That y value down there is negative 1. Negative 1 times 3 is negative 3. Okay? So for the graphs that I've provided, each line on the y-axis is 1 unit. No, you're fine, you're fine. Okay, each line is like 1 unit, and then as we count across, every 2 boxes is pi over 2. All right, so let me shrink this a little bit so it's all on one screen. We can kind of take a look at that. All right. All right, any other questions, or would we like to move on and see another example? Okay. All right, let's move on to example 2. Okay. All right, so example 2, let's put a big star next to example 2. Okay. This is a form that we've seen a lot in Math 116. And I was like, I need you to know how to factor. I need you to know how to factor. I need you to know how to factor. And not just know how to factor, but know when to use it. Okay. And so what we need to do with this kind of question, and I'm looking for you to write this on your exam, okay? So in order to prevent Judy's questioning about where you got your miracle answers from, please show me the following step. We have to factor out this 2. Okay? You have to show me this step. Some of us are showing the step and it's good, everything fits. Some of us have sort of avoided showing this step and then gotten, surprisingly, the correct answer. Okay? So that kind of stops now. We want to make sure we know how to do this part. So when I factor out the 2, I'm left with an x here. But what am I left with for that second term? Okay, well, if I have 1/2, if I distribute that back in, I'm going to get 1. Ah, okay. So let's modify that to be pi over 2, okay? Yeah, when we have the pi over 2, now when we distribute that 2 back in, we get 1 pi, okay? So make sure that you show me this step. So important. Okay, now when we go back to our order in which things occur, all right, let's see what we have. In this case, we have a C value, okay? We have a shift to the left pi over 2, right? And that's our horizontal shift. And then we have 2 waves where there was 1. Or as other folks have said, it's a horizontal compression, okay? So those are the 2 things that are happening here. I have to move the graph to the left, and then around the center point, I have to sort of collapse in, okay? So let's start with our parent function. We've got f of x equals sine x. And I'm gonna graph that over here. So we've got 0 and 1 and 0 and -1 and 0. And same thing on the other side. Okay. And that is something that we want to get pretty familiar with graphing, okay? Please don't be sloppy with your graphing and just kind of like draw some like waves on a piece of paper, okay? Please plot out these points. All right, so we have that pi over 2. So that means f of x equals sine of x plus pi over 2. So that's the first piece that we're going to take. We're going to move everything to the left. Now, if we think about our center point, it was right here, and then I just picked another point sort of next to it, and I'm going to move those points to the left, pi over 2, okay? So if I move the blue point to the left, pi over 2, it's right here. Good thing we're already counting with pi's, right? We can literally count pi over 2. And if we shift that purple point, it's going to become over here, right? We're just sliding everything over to the left. So left, pi over 2, okay? And then we form the rest of the graph around this. After the purple point, what should the y value of the next point be, the next nice point? All right, so if we throw like a yellow point on here, where does that yellow point go to? Pi over 2 comma 0, good, exactly. Everything moves over, okay? Now you're welcome to sort of color code all of the points if you want. I typically just do a few to kind of get the hang of how things are moving. Okay. But I think we can see when we sort of track the points that we get, yeah, exactly. We get actually cosine. Okay, so we'll talk about that in just a moment, but this graph happens to be the cosine graph, okay? But more importantly, we can see that we've just moved every point to the left pi over 2, all right? Now, let's see, our last thing was we're gonna do 2 waves where there was 1. So a horizontal compression, all right, a horizontal compression, that means the points are half as close together, right? So we're squeezing everything in, but where do we squeeze from? We squeeze from the new center point. So our center point, that blue point, is gonna stay, okay? That's important to know. The center point does not change when we're compressing horizontally. Everything compresses around that, okay? So this purple point moves in half as close. It was 2 boxes away, now it's only 1 box away. The yellow point moves into here. So we just kind of scooch everything in, all right? We've got our yellow, our purple, and our blue, okay? And if we keep following that pattern, all right, we can see that before we had 1 wave that was 8 boxes long, and now we have 1 wave that is 4 boxes long, right? So we've compressed the wave to be half as long, and so our points are closer together, and it means that we have more waves in the same spot, right? So that's example number 2, all on one page, okay? Making sense? Not making sense? How we feeling out there? Why we start where? At the blue point? Yeah. So just like we think about like the center point in a parabola as the vertex, we want to make sure that we keep track of that center point because things always move around the center point. Okay, so whatever you pick as your center point, keep track of where that is so that we know that things move around it. Okay. If we think about this equation right here, this one, okay, what value of x makes that 0? Like, when is this true? Okay, so x would equal negative pi over 2, right? Like I just moved the pi over 2 to the other side. That means this is your new center point, right? And so everything happens around that point. Does that make a little bit more sense? Okay. All right. I think I was just trying to shortcut it a little bit. Like I didn't want to add the extra part, but I think that does, the question you ask is great at clarifying like why the center point? Well, it's the new 0, right? We moved it over. Where did it go? It went to negative pi over 2. Okay. All right, any other questions here? Okay, so let's do this. I'm going to all right, so one more example with sine. This one does not include the phase, not the phase shift, but it doesn't include that factoring part that I made a big deal of in number 2, okay? But I know that some of the homework questions or some of the quiz questions do want you to take a look at that factoring part, okay? So if we kind of preview what we have here, we know we have these 4 graph transformations. And in this case, we do have a phase shift. We're going to move to the right pi units, okay? And then there's no horizontal compression here, all right? We do have an amplitude change. So we're gonna multiply all the y values by 2, or we're gonna stretch it all out by 2 vertically. And then last but not least, we're gonna move down 1 unit, okay? Are there any questions about where I'm getting these numbers from? So then we start with our good old friend sine x. What comes next? Well, we're going to have sine of x minus pi, or that means we move to the right pi unit. We have a vertical stretch of 2, which is because of this 2 in the front. And then we have a vertical shift down 1, and that is the -1 at the end. Okay, so I just set this up a little bit differently than the other one. So instead of sort of doing the graphs piece by piece, I just filled in all the equations first. Play around with what order works best for your brain. Do you want to map it all out, or do you want to just take it one transformation at a time? Okay, that's really up to you. Either way, when we get to the graphs, we want to make sure that we can sketch our parent function graph of sine fairly quickly. Okay, so we have our parent function. Let me put in, are the colored dots helpful, by the way, or are they just like distracting? Is that a yes, they're distracting? Oh, helpful, okay. All right, so let's go with maybe 3. Blue, let's go with pink to make it a little bit different, and yellow. Okay, so we're going to take all 3 of these points and we're going to move them to the right pi. And if you're not sure, well, how am I supposed to count by pi? Look at the numbers on the x-axis, right? The blue point is literally moving to where it's labeled pi. So I would try not to like let yourself worry too much about like, oh, I don't know how to count by pi. A lot of these, all these grid lines are already marked for you so that it should be a little bit easier to figure out where it goes, okay? Now the pink point is gonna go here and the yellow point will go here. So pink, yellow. Now I've got that bump, okay? When I try and fill in the rest of this, at pi over 2, should my point be at +1 or -1? Okay, so here, should the y value be +1 or -1? Good, it's gonna be -1 because if we were to add more colored dots, it's this point down here, right? That point also got moved over. And let me get rid of that circle so it doesn't interfere with the graph, but I go down. Then I have to stop at 0, 1, 0, -1, 0. Okay? So it is a lot of repetition of 1s and 0s and -1s. It's a lot of repetitions of 1s and 0s and -1s, but we want to make sure that we're stopping at 0 in between the 1s and the -1, okay? And then we can kind of connect everything. Whoa. All right. And so that is our shift to the right to the right pi. It does not start at 3 pi over 2. It starts at pi. The blue point here, they went to pi. Yeah? Okay. All right, let's see what happens next. All right, so now this is when it's not reflected. We literally just moved all the points. Like this blue point moved there. The pink point moved there. Like everything moves by pi. That's okay. I think that's why it might be helpful to keep track of the points, because if you just look at the difference in the pictures, you might think it's a reflection, but it's not a reflection, it's a horizontal shift, okay? So keep track of those points. All right, so now what is the one point that I can already draw for this third graph? Because it's gonna stay the same. Like everything else is gonna change, but yeah, that center point is gonna stay. Okay, now the pink point in the graph above is 2 boxes away, or it's pi over 2 units away. But now I want it to be half as far away. It's only going to be 1 box away. The yellow point was 4 boxes away. The yellow point will now be how many points away, or how many boxes away? Yeah, it's going to be 2, right? Because everything is half as far away. All right, so it does look a little bit more squeezed, but we just fill in all the other points with our pattern of going between 1 and -1. Okay. And so now we have a point that's 1 box away when it was 2, and we have a point that's 2 boxes away when it was 4. Okay, so Yuthan, yeah, if you reflect it and you move it, yeah, those are going to be equal. And so what you really uncovered there is this is part of the reason there's so many identities in trig, like statements that are always true. Because these waves repeat, we can actually have a lot more things that are equal to each other than some of the other functions like x squared or x. Okay? Oh, good, I'm glad. All right, we got one more transformation here. We're taking every single point and we're moving it down 1 unit, okay? So the blue point moves down 1 unit. The pink point moves down 1 unit. The yellow point moves down 1 unit. every point moves down, right? If I wanted to throw an extra one, this green point will also move down, okay? And then it's just about following that pattern. And connecting your dots. Okay. So let's see if we can get that all on one screen. All right, so if we keep track of those points, that helps us keep track of whatever transformations we're doing, okay? All right, now, like pretty much everything else in math, if you feel like you're finally getting it, we're gonna introduce a new thing. We're gonna introduce a new function. Okay, yay! So we've looked at the graph of sine, right? And we've taken this graph of sine, we've moved it all around. We've shown that we can do the same graph transformations that we did before, okay? And now we're gonna extend that even more, all right? So here is our friend, the cosine graph, okay? And when we think about the domain of this graph, we know that it's gonna be the same as the domain for sine because the waves keep going forever and ever. And another way that we could write that was all real numbers, or that fancy script R. Okay, mine's not that fancy. I just put a second line down the R. Now, Vanessa, I think it was earlier, had some great feedback about what our range was. She said that the highest point was 1 and the lowest point was -1. So that helped us establish the range, okay? Can we say that the range of cosine is also from -1 to +1? Like, is that a fair statement? I'm glad you find it fancy. Yeah, we can say that that range is exactly the same from -1 to +1, because this is the highest y value and this is the lowest y value, okay? Now, we know, hopefully, from last week that cosine is even, right? And I showed you on a unit circle how it's even. And hopefully, at least I meant to say it out loud. If I didn't, I said it in my head. That when we get to the graph of cosine, it might be a little bit more obvious why cosine is even. If we fold the left half and the right half over here, we sure get the same thing on both sides, right? Yeah, they have the same y value. So we have right here extra confirmation that it's even because, for example, if we said cosine of pi is -1, but cosine of -pi is also -1, right? Same y value, but opposite x values. Okay. Now, at the beginning of this lesson, when we started talking about sine, I was like, okay, let me just like shade in this wave. Is this a wave? And the blue one that I did, a lot of folks were like, that's not a wave, okay? But the reason why I picked that one is because this is what we traditionally think about as a wave for cosine. We start at 0, we go down, we come back up, and we stop at the top. So we start at the top, we stop at the top, okay? This is one wave of cosine, okay? Can we say that this pink one is a wave? Yeah, maybe that's like how we more easily think about it as a wave, but the pink one is a wave, and separately, the blue one is also a wave, all right? So we know that one wave takes 2 pi to happen. So the period is 2 pi. Okay. All right. Any clarifying questions about the graph of cosine or any of the features of cosine? Okay. All right. How do we feel about one example of graph transformations for cosine to kind of seal off today? That sound good? We all still there? Maybe, maybe not. Okay. All right, now I did include this here so that you could sort of annotate on your own, like what does the A stand for, what does the B stand for, what's the C stand for, what's the D stand for, okay? The thing to keep in mind is this one has a cosine, but you could write the same thing with the sine. All right, so let's do this one. I think this will be a good one to end on because first of all, it brings back that factoring thing I told you about, but it also gives us a chance to look at that reflection piece, and we haven't seen an example like that yet, okay? So one thing I would 100% expect to see on an exam or on a quiz is for us to know that we need to factor that 2 out. And that we're going to take the time to do that so we can identify the correct horizontal shift or phase shift, okay? Now I'll do the easy part. I know there's an X here, and I know there's a minus. You guys help me out with the hard part. What is left there once I factor out a 2? Let's see, pi over 4, okay. Well, you know, off to the side, I might just multiply those out just to test for myself. So 2 times pi over 4 gives me 2 pi over 4, which is pi over 2. Okay, good. So we did that right. Okay. So this is the thing in the blue is just a way for you to kind of check whether you factored correctly or not. Okay, you don't have to show me that work, but if it helps you connect the, bridge the gap between like, how did we get here? You could always check it that way, all right? All right, now if we think about our parent function, we're gonna start with cosine this time. And the first thing we're gonna do is we're going to shift everything to the right pi over 4, okay? Because we're working with the C value first. Then after that, we have our horizontal compression of 2, right? That's our B value. And last but not least, we have that negative sign in the front. And I think it was Richard who said earlier that negative sign in the front is going to give us a reflection over the x-axis, okay? So finally, we'll have a reflection over the x-axis, and that is just the negative sign in front. Okay. All right. So let's get started graphing these, okay? So we're going to start with that parent function, and if you start doing this, I'm going to be real disappointed, okay? This is the graph of sine, what we have right now. And what we want to draw is the graph of cosine, which does not go through the origin, okay? Yeah, that's wavy, but it doesn't cross at the same point, and that's where we need to be precise and accurate, okay? So we start at 1, we go down to 0, down to -1. Oh, now time to turn around. 0 and 1. Okay. I know it's kind of weird to draw a wave that starts at the top and finishes at the top, right? But it's kind of good to practice it. And then we do the same thing on the other side because we know it's even. All right? All right. Now, there's a couple things that are tricky about this problem. One of them is that I'm moving pi over 4, and we haven't seen that yet. All right, so how many boxes is pi over 4 on this graph paper? It is not a half a box. Let's see, if I go 2 boxes, that's pi over 2. So it's not 2 boxes. Pi over 4. Well, that's half of pi over 2, right? So pi over 4 on our graph paper is equivalent to 1 box. Okay? So that means if I set up those colors again, center point, next point, next point, we're going to move them all to the right 1 box. Not 2, not 4, not 7, just 1 box. Because 1 box is pi over 4 on your graph. Okay? To the right, to the right, to the right. Okay? So let me just pause here for a moment. I know that fractions, I know that pi, fractions with pi can make people kind of nervous. So are there any questions about how we figured out we're moving 1 box? Okay. All right, let's move on. What is the 1 point that's going to stay in this next graph? Right, we've got a bunch of points from the previous graph, the blue one, the pink one, the yellow one. Which one is going to stay? Yeah, that blue point, right? Our center point stays. Everything compresses around it, right? So this blue point is going to stay, but the pink point is now going to be 1 more box in. The yellow point, instead of being 4 boxes away, is now going to be 2 boxes away. And if we finish that one pattern, which I think was Eric's suggestion, that you draw 1 wave and then you fill in the rest of it, right? Here's our 1 wave. It did take us, whoops, we would have finished in 8 boxes. And now we finished in 4 boxes, okay? And so let's complete that. All right? So we squeezed in everything twice as close together. And now we've got one more transformation, and that is we're going to reflect over the x-axis. So this blue point, will that stay or will it change? All right, where's that blue point going to go if it changes? I agree that it's going to change. Where is it going to go to? Yeah, instead of being up above the x-axis, it's going to be below the x-axis, right? Basically, I'm going to flip all of the points I drew. So we've got our yellow one up here now. Our pink one is still in the middle, and the blue one is now down here. Okay, and then from there, you could fill in all the other parts. All right. And presto bingo, we've got our final picture. Let me just, whoops, zoom in so you could see the whole thing on one page, okay? So we've kept track of every single point along the line so we could really see what was happening to the graph, all right? So that's it in terms of our lesson for today. I think you'll find that the quiz number 6, I believe, is very similar to these. It's just a whole bunch of graph transformations. You are welcome to use Desmos to check your work, but I do want to see each one as you go, and I do want to see your process of thinking. Okay, so make sure that you show that to me, that you're getting in a habit of like knowing what's expected on an exam, so that we don't lose any silly points for not showing process. Okay. All right, any questions before we take off? All right. Well then, folks, we will stop our video